All right, we're going to start chapter 5 now. Chapter 5 is a continuation of what we've been looking at, just trying to find derivatives or find shortcuts or different methods to finding the derivatives of different functions. In chapter 5, we're going to be focusing on two types: exponential functions, or exponential and logarithmic functions, and trigonometric functions. And within, now specifically exponential functions, we're going to have two different types. One is when the base is any number, right? When you have a number as the base. And the second type is when you have a special case, which is where the base is a very specific number known as Euler's number, which is e. It's a 1.27 and it goes on like that. But when you have a very specific number, which is like 1.27, it goes on to the power of x. Now obviously you can't put that number in. It's like pi. Pi is 3.14159 and it just continues to go on and on. So instead of writing that entire number out, we put pi. This is also a number that has a very specific meaning and a specific usage, which we're not going to focus on right now, but it can be written as e. So 1.27 and so on and so forth becomes e. So e to the power of x is what we're going to focus on today. Right? We are going to be starting with exponential functions and finding their derivatives, and the introduction to that will come through y equals e to the power of x. So if we have a function f at x is equal to e to the power of x, the derivative of e to the power of x is e to the power of x. This is why it's a very specific and very special case where it is its own derivative. To get an understanding of why, let's take a look at the function itself. This function in the negative area, so from the left to the right, it is a small positive number. What's the derivative? What is the slope of this tangent? A small positive number. Then a larger, and it's a positive number that's getting larger and larger and larger. So if we were to graph the derivative onto this same function, it would be a small, in the far negative, small positive number, which gets larger and larger and larger. Now all exponential functions follow the same pattern, but when the base is e, that's the only time where the derivative is exactly the same as the y value in an exponential function. It's a very special case scenario. What we're going to do now is look at how you apply the different rules of finding the derivative to this specific type of exponential function, which is when y is equal to e to the power of x. Okay, so the first example now is when we have y is equal to e to the power of 4x. This is an example of how you apply the chain rule, where you have a function which is 4x inside of another function which is e to the power of a value. So it can be, you can think of it as y is equal to e to the power of f at x, and f at x is equal to 4x. So this function is inside the y function. So if you're going to find the derivative using chain rule, remember what that process is like. You find the derivative of the outside and multiply by the derivative of the inside. The outside in this case is e to the power of something. Now what's the derivative of e to the power of something? It is e to the power of that same thing. It doesn't change. So e to the power of 4x, the derivative is e to the power of 4x multiplied by the derivative of the exponent, or the derivative of what's inside. Remember, that's the chain rule. So multiplied by 4, so it'd be 4e to the power of 4x. That would be the derivative of e to the power of 4x. Okay, let's try another one. Okay, next one. Next example is y equals x squared times e to the power of x. This is an example of product rule. So you have x squared, which is one function, multiplied by e to the power of x, which is another function. So these are two entirely separate functions being multiplied, so we're going to use product rule. To find the product rule, you take the derivative of the first term, 2x, leave the second term as it is, so 2x times e to the power of x, plus, now the first term stays the same, multiplied by the derivative of the second term, which is e to the power of x. Now what do? We can factor out e to the power of x, and we can factor out one of the x's. So we'll have x e to the power of x multiplied by 2 plus x. That would be the final derivative in its simplified form. Okay, let's do one more example. Okay, this is example 3 from the textbook. We have f at x is equal to 3e to the power of x squared. We got to find f of negative 1. So again, now we have a power rule as the exponent. So this is now chain rule involving x squared and e to the power of x squared. To find the derivative, understand, remember, we can ignore the 3. The 3 is not part of the derivative. It's just on its own on the outside. To find the derivative of e to the power of x squared, we're going to find the derivative of, so that's just e to the power of x squared, because you take the derivative of the outside function, which is e to the power of something, so it stays the same. Then you multiply it by the derivative of the exponent, so that's 2x, and that would be your derivative. And now you want to find f inverse of the derivative at negative 1. So we have 3e to the power of negative 1 squared times 2 times negative 1. So e to the power of negative 1 squared, that just becomes positive 1. So it's 3e times negative 2. So we have 3 times negative 2 is negative 6e. Okay, if you're putting your calculator, it might transform into a decimal for you. I would prefer that you leave your answers like this in a simplified form to avoid rounding and decimal errors. Okay, so again, very straightforward section. You're looking at how to find the derivative of an exponential function when the base is a very, very, very specific value, which is e.